You ever stop and think about what's really going on inside your computer? Today, we're going to go behind the screen to uncover the secret life of a process.
I mean, seriously, think about it for a sec. Right now, you might have an email open, maybe some music streaming in the background. Notifications are probably popping up, and a file's downloading. It all just works. It feels so smooth, right? So, how in the world does one machine juggle all of that without just breaking down? Well, the answer isn't actually magic, but honestly, it's just as cool. It's all thanks to this incredible high speed ballet that's being managed by your computer's master conductor, the operating system. So let's pull back that curtain and see what's really going on.
All right, first things first. To understand this whole show, we need to get to know the main character. What exactly is a process? Okay, so think of a program, the actual application file for your web browser, as a recipe in a cookbook. It's totally passive, right? Just a list of instructions sitting there on your hard drive. But the moment you double click that icon, your computer loads it into memory and it starts running. That's when it becomes a process. It's now an active thing. The chef is in the kitchen, actually cooking the recipe. And get this, just like you can cook the same recipe over and over, you can launch one program to create tons of different processes. Think about opening multiple tabs in your browser. Same recipe, multiple dishes cooking at once. So if you've got potentially hundreds of these active chefs, all running around at the same time, how on earth does the operating system keep track of them all? Well, this is where the process's official ID comes in. Every single process that gets created gets its own little passport. In the tech world, we call this a process control block, or PCB for short. It's basically a special file where the OS jots down everything it needs to know to manage that specific process. So what's inside this passport? Well, for starters, the PCB holds a totally unique process ID, the PID, so it can tell all the processes apart. It's also tracking the process's current state, like is it running right now or is it just waiting around? And it doesn't stop there. It also knows its priority level, all its memory info, and any I/O devices it's talking to, like your keyboard or the disk drive. The PCB is, without a doubt, the single source of truth for every single process. And speaking of memory, each process gets its own private little workspace to play in. You've got the text section, which holds the actual program code. The data section is for fixed variables. Then there's the heap. You can think of that like a big, flexible storage closet for all the stuff the process needs while it's running. And finally, the stack. The stack is like a super neat pile of plates for managing function calls. The last one you put on is the first one you take off. It's this incredibly organized little system inside every process. Okay, so now we know what a process is and how the OS keeps track of it with that PCB passport. So let's follow one on its journey. It's a pretty dramatic, super fast-paced trip from the moment it's created to the moment it's done. Let's dive into the process lifecycle. You can pretty much map out this whole journey using a classic five-state model. First up, a process enters the new state. This is when it's just being created. Once it's all loaded up into memory, it moves to the ready state. Basically, it's standing in line waiting for its turn on the CPU. Then, when it finally gets picked, bam, it enters the running state. This is showtime. This is where the actual work gets done. Now, if it needs to wait for something, say a file to be read from the disk, it gets moved to the waiting state, which some people also call blocked. And then finally, once its job is totally done, it enters the terminated state. And that's a wrap. But here's the really crucial part. This is not a straight line from start to finish. Not at all. A process might get a tiny, tiny slice of CPU time, then get kicked from the running state right back to ready. Then it gets picked again, does a little more work, then maybe goes to waiting because it needs some input from you. Then it goes back to ready again, and so on. It can literally cycle through these middle states, ready, running, and waiting, thousands of times a second. The new and terminated states, though, those only happen once in its entire life. Okay, so who is making all these decisions? Who's the one deciding which process gets to move from that ready line to the running state? Well, that is the job of the master conductors of the whole operating system, the schedulers. You see, the OS uses a whole team of schedulers to run the show. You've got the long-term scheduler. This one decides which new jobs to even let into the system from the disk. It works pretty slowly, and its main job is to control just how many processes are active at any given time. Then you've got the short-term scheduler. This one is frantic. It's the one picking the very next process to run on the CPU from that ready queue. It has to be unbelievably fast. And sitting in the middle, you sometimes have a medium-term scheduler which can temporarily swap processes out of memory to make some room, kind of managing the overall load on the system. Let me put it another way, because this is a great way to think about it. The long-term scheduler? It's like a bouncer at a really exclusive club, carefully deciding who even gets to come inside. Meanwhile, the short-term scheduler is the traffic cop at the busiest, most chaotic intersection you can imagine, making split-second decisions about who gets to go next. Both are absolutely vital for keeping the whole system from grinding to a halt. So we have these schedulers, but they're not just picking processes at random. Nope, they follow a really strict set of rules. So how are these incredibly critical decisions actually made?
It really boils down to two main philosophies. First, there's non-preemptive scheduling. In this world, once a process gets the CPU, it keeps it until it's either completely finished or it voluntarily says, okay, I'm done for now. But then you have preemptive scheduling, and this is what pretty much all modern systems use. Here, the OS can forcefully interrupt a running process, kick it back into the ready line, and give the CPU to a more important task. This right here, this is the secret sauce to responsive multitasking.
You know, any good scheduling algorithm is a huge balancing act. On one hand, it wants to keep the CPU as busy as possible, no wasted time, and it wants to complete the maximum number of jobs over time, which we call throughput. But for you and me, for the user, the most important goals are minimizing waiting time and response time. That's what makes your computer feel fast and snappy when you click on something.
All right, let's take a step back and tie all these pieces together. How does this whole secret, hidden world of processes, states, and schedulers create the seamless experience we have every single day?
So when you really put it all together, what does it all mean? It means that every single click you make, every keystroke, every notification that pops up, all of it works because of this invisible, super high-speed dance going on under the hood. Processes are born, they wait in line, they get to run for just a few milliseconds, they get interrupted, they wait for some data, and then they do it all over again, all managed by schedulers making thousands of these decisions every single second. This is the fundamental engine that makes modern computing possible. It's amazing.